Good day, class. So for today, you're going to learn a new type of higher order differential equations, the non-homogeneous higher order differential equations. And then later on, you're going to determine the solution of such using the method of undetermined coefficients. So let's move on. When we speak of a non-homogeneous higher order differential equation, the right side of that particular higher order DE is a function of the independent variable. In the case of the second order higher order differential equation, the coefficients here a, b, and c are all constants, and this g of x is a function of your independent variable x. Now y prime here and y double prime tells you that your unknown function is y and your independent variable is x. So the solution of a non-homogeneous higher order differential equation comprises of two parts when we use the method of partial fractions. The first part is based on the complementary equation, which is just but the same equation as your given non-homogeneous DE, except that this time you set the right side equal to 0. Now, your original non-homogeneous higher differential equation is now converted into what we call a complementary equation. The complementary equation will yield the roots of this particular equation, just like the way we have done it with homogeneous higher order differential equation, and the roots will tell you the form of the complementary equation. That's just one part of the solution of a non-homogeneous higher order differential equation if we use the method of undetermined coefficients. Now, I'd like to move forward. So, in here, if we use the method of undetermined coefficient, the solution of our non-homogeneous differential equation will have two parts. Your complementary equation or solution, which is y sub c of x, and your particular solution, which is y sub b of x. Now, your independent variable here is x and your unknown function is y. Your y sub c is determined just like the way you determine the general solution of a homogeneous higher order differential equation. That was our lesson last week. Now, the y sub b, on the other hand, is based on the function that appears on the right side of your non-homogeneous DE. Now, the reason why the method of undetermined coefficient is more straightforward, easier to work on, is because it doesn't use any integration in the process of finding the particular solution. It will only use root finding, algebra, that is specifically on working on equations, systems of equation, to find the values of the undetermined coefficient. Now, however, the g of x on the right side is very limited or restricted if we use this particular method. It can only come in the form of a constant, an exponential function, a sine or a cosine function, a polynomial, or the combination of this or a combination of the product of this. If your g of x contains other transcendental functions, or shall I say a square root function, then that particular method of undetermined coefficient will not work already. So our focus for today is just for functions that can be solved using the method of undetermined coefficients. For those functions which cannot be processed using this method, that would be processed using variation of parameters or the operator method, which will be relying on integration. So now let's go to non-homogeneous higher order differential equations with constant coefficients. Even if your higher order DE is already non-homogeneous and linear, but the coefficients of the derivatives of your unknown function and even the unknown function itself are not constants, the method of undetermined coefficient cannot be used as well. So it's also limited and restricted to these types of functions in which the coefficients are all constants. Now, so this is the form again for a second order DE of our non-homogeneous higher order differential equations with constant coefficients. Okay, and it is said to have two solutions, or rather two part for its complete solution, and that's the particular solution and the complementary solution or equation. Now, let's start with something that is very simple, and that is the right side of your non-homogeneous DE is a constant. In this case, here it's 1000. Now, if you will simplify the form of the derivatives here of your unknown function and the unknown function itself, it would be this. And I'd like to set it to 0. Now, based on this particular equation, I can write what we call as the auxiliary equation, wherein I have set to 0 the g of x on the right side, which is in this case a constant 1000. So I set it to 0. The purpose is for me to know the roots of this particular equation. So since it's a third degree polynomial, we are expecting that we will have 3 roots. One is 5, and the other one, if we take the square root of negative 25, is a pair of conjugate imaginary roots. I say conjugate because one is the negative of another. So a pair of conjugate imaginary roots. Now you know already how this works, because in the method of handling homogeneous higher order differential equations, you simply base the form of the general solution on the nature of the roots. So if it's real, the real root becomes the exponent or the argument of an exponential function. If it's imaginary, it becomes the argument of a pair of sine and cosine function. Now, by the way, the manner in which you write the cosine, the sine, and the exponential function need not be in this form. They could be interchanged. What is important is they are all present in your complementary equation or complementary solution. So this is now just one part of the complete solution of your non-homogeneous DE. Now, the next part is in finding the form of the particular solution. So when we like to find the form of the particular solution, we base it on the g of x. In this case, it's g of t. And by the way, you have to be very careful when you write your variables in your DE. Now, in this case, your form for the complementary solution should be in the form of q as a function of t, not y as a function of x, because your variables here are q and t. So when we write the form of the particular solution here, your particular solution is a function of t. That is why it's written as q sub p of t. Now, since it's a constant, we will represent it by an arbitrary constant a, which we will later on determine. So the first part in finding always the particular solution is you write the form of the particular solution. Then you need to differentiate it depending on the derivatives that appear in your differential equation. So we have until in this case, the third derivative. So we need to differentiate this constant 3 times. However, class, any constant has a derivative of 0. So all the terms here, this one, and this one, would all be 0, except for this q, which will now be represented as a. So your q sub p is equal to a then. So it would be then negative 125a, replacing the q in the previous equation by a, equal to 1000. The 1000 is the exact function, in this case a constant, that is written on the right side of your DE. The purpose of this is for you to find the value of this undetermined coefficient, and that's negative 8. If you know already, and since this time you know already that it is negative 8, then in terms of the form that you have originally written, you need to substitute this one. So your q sub p is equal to negative 8. Now, the complete solution using the method of undetermined coefficients for our higher order DE then will constitute the q sub c and the q sub p, which we have added. So this is now the solution of that particular higher order differential equation, in which your g of t is a constant in the form of 1000. Okay, another solution or another type of function that the undetermined coefficient can also process is the polynomial. You see this x squared here, so it could be viewed as a second degree polynomial. Even if you don't see an x here and a 1, this is still to be viewed as a complete polynomial when we process this original higher order DE using the method of undetermined coefficient. So for example, I write here x squared plus 1. It's still to be completed as if it is having an x squared, an x, and a 1. Or even if your polynomial here, for example, is just x cubed minus 2, it is still to be completed in terms of the form when we write later on the form of its particular solution. But nonetheless, we will always start with determining the complementary equation or solution, and that would lead us to setting the right side 0 and finding the roots of the auxiliary equation. You can find the roots using synthetic division or simple factoring, whichever is easier to do and applicable. So in this case, your roots are 1 and negative 2. Both are real and unique. So when you write your complementary solution, then they will simply be exponential functions in which the arguments are 1 and negative 2, or x and negative 2x. But this is just one part. Now this x squared will have to be represented in the form of ax squared plus bx plus c. So notice, class, that I have completed all the terms that should appear in a second degree polynomial, even if what you have in the original D is just an x squared. Now what you do with this, you need to differentiate it twice because your given DE has the first and the second order derivative. So taking the first derivative of this is 2ax plus b, and taking the derivative of this is 2a. Now having this second derivative, first derivative, and the form of the particular solution, you can now go back to your original DE, and that original DE, by the way, is this, and then copy what's on the right side of that particular original DE. So in this case, this is now our resulting equation. We have substituted the derivatives of our particular solution form and the particular solution itself in the original differential equation. Now, the purpose for this is for us to be able to equate the coefficients on the left side and the right side of the equation. What do we mean with coefficients? Like, in this case, you have an x squared and you have an x squared here. You will equate the two coefficients. So, that would be best explained on the next line here. Before we can do that, you can also simplify the left side here. So you have now 2ax squared, and then the x term will be negative 2b and 2a. So you have here, and your constant is 2a plus b minus 2c. So this is now your simplified expanded equation, okay, equivalent to what you have on top. When it's written like this, it's so easy to equate coefficients. So this one is x squared and this one is x squared, so you equate the two. You don't have an x here, so this coefficients here will be equated to 0. You don't have also a constant here, so this set of constants will also be equated to 0. So the resulting equations would be this. And if you work out these three equations, the values of a, b, and c are this. Actually, these are your original undetermined coefficients, which you now were able to determine the coefficients. So since you know already a, b, and c, you can substitute these undetermined constants or coefficients before in the original form of your particular solution. Now, your solution then will comprise the yc and the yp. So in this case, that would be this one. So you copied the complementary solution and added it to this particular solution to get the complete solution. This is for our example number 2. Okay, so this is your complete solution for sample problem number 2. Now, for example 3, this time your g of x would either come in the form of a sine or a cosine function, or it could come with both sine and cosine function as long as the argument of these two functions are the same. So in this case, it's just the sine of x. So you always start with finding the, let's say in this case, the complementary solution or the complementary equation. So for a change, well, let's say start with the form of the particular solution, in this case wherein you have a sine function on the right side. So the form of your particular solution will comprise of the pair of the sine and cosine function written in this manner. By the way, you can have the sine here and the cosine in here. It doesn't matter as long as you have both functions in the form of your particular solution. You need to differentiate this twice because you have until the second derivative here. So if you differentiate this, you will have a negative a sine x and a b cosine x. And if you differentiate this, that would be the second derivative, a negative a cosine x and a negative b sine x. These three should be substituted back to the original dE to enable us to find the undetermined coefficients a and b. So this is now the original d in which you have substituted the derivatives of your unknown function and the form of the particular solution. Okay, now if we will simplify, it would something be like this. We grouped all the cosines, the terms that has the cosine, and we grouped the terms that has the sine. The purpose is for us to be able to equate coefficients. So in this case, your sine x here, which is having a coefficient of 1, should be equated to negative a minus 3b. You don't have a cosine x here, so this negative 3a plus b should be equated to 0. Okay? And that's this one. And then you work your way through these two equations to solve for the two coefficients a and b, and the values are these two. Now, knowing a and b, you can go back to the form of the particular solution and have it substituted there. Now, you're done with the particular solution, you can find the complementary solution, which in this case is just the roots of the auxiliary equation on the left side, or made from the left side of your differential equation. Your complete solution would be the sum of the two. This 1 over 10, by the way, is in here. So it's negative 1 over 10 cosine 3 cosine x plus 3 sine x. So we have factored out here negative 1 over 10. Okay? So that's for the third type. You have a sine or a cosine function, or both sine and the cosine function in the right side of your differential equation. The fourth type is when you have an exponential function. Exponential. So your particular solution will have a form written copying your original exponential function and multiplying it with the undetermined coefficient or the constant a. Okay? You copy the original exponential function. That's how we do it. So if this is e raised to negative 3t, this would be e raised to negative 3t. You just multiply it with the a. Then again, differentiate it depending on the derivatives that are present in your given dE. So this is the first derivative of this, so 2a e raised to 2t. And the derivative of this derivative would be 4a e raised to 2t. Okay? If we will substitute this 3 in here for the derivatives and the unknown function itself and equate it to what is written on the right side, we'll be able to find the a, the value of the a, which is negative 1/2. So this negative 1/2 now will replace the a here in the form which you have originally written for your particular solution. Again, notice that your independent variable is t, so you don't use x but rather t when you write your solution. So this is your particular solution. As to the complementary solution, that would be dependent on the roots of this left side of your dE when you write it in the form of an auxiliary equation. So your roots are 4 and negative 1. So this will be your complementary equation. This can be interchanged. And this is also, you see, I already made the mistake here. So this should be a t. And in here, you will have the sum of the two. So this should be 4t e raised to negative t equal to 1/2 e raised to 2t. Okay, so this should be a t, not an x, because we're given an independent variable t. Okay? So this is for our fourth type of DE. The fifth constitutes of the product, the sixth and the fifth and the seventh example constitute of a combination of the functions that were discussed in the first four examples. The combination can be a single combination like a simple adding or a subtraction of this function, or it could be the products of these functions. So as an example in here, you have the product of the cosine of 3x and an x. So when you write the form of the complementary or rather particular solution here, that will marry or that will combine the two forms. One form for the cosine function and one form for this first degree polynomial. For the cosine, we know that it should be a cosine 3x and b sine of 3x. And since this cosine was multiplied to an x, the original a and b here was replaced by the form of the particular solution of this first degree polynomial. So you write ax plus b and cx plus d. You don't write here ax plus b as well because we know that the arbitrary constant here for the sine of 3x is different than the arbitrary constant of the cosine of 3x. Though in form they are the same class, they are the same, but the coefficients of course should not be the same. So this is how you should write in terms of combinations or products of two functions. I'd like to give you a simple example, starting with the product of an exponential function and a cosine function here. And you will have to write its particular solution in this form. You copy the exponential function because that's what we do when we're given an exponential function. But instead of multiplying this exponential function by an undetermined coefficient, you replace that undetermined coefficient by the form of the particular solution of this cosine. And that's a cosine 3x and b sine of 3x. At first glance, class, this is really the form of the particular solution. But we will have to be very careful before we go to next processes, and that is differentiate this, because at times there's a need for us to modify the particular solution based on the form that we are getting for our complementary equation. And that is what is present here on the left side. What do I mean? Okay? Now, if you will process the auxiliary equation on what's written here on the left side, this would be yielding this quadratic equation with these complex roots. So you have a 2 plus minus 3i. As learned in the handling of the solution for homogeneous DE, when your roots are complex, the form of the solution, the general solution for a homogeneous DE then is e raised to 2x. So this would be using this particular real part, and the imaginary part here will be represented by the cosine and the sine function. Now, if you look very intently in this form of your complementary solution, class, it's very similar to the original one that we have written here. The only difference are the arbitrary constants. So in this case, class, you need to modify your particular solution because in terms of form, they are really the same as that of your complementary solution. Now, the question is, how do you modify? So we modify our particular solution by multiplying it with the independent variable. It depends on how many times you multiply all the terms in your complementary solution. As long as all the terms in your complementary solution and particular solution are not the same. There shouldn't be any term that is the same in form. So I wrote here that you need to multiply by x because your independent variable here is x. If your DE is having an independent variable t, then your multiplier here, of course, will be t. Because it doesn't make sense when you multiply a DE, which has an independent variable t, with x. What will x do there when your independent variable is t? So the manner you modify your particular solution is in terms of multiplying it with the independent variable. So it could be in terms of x only or x squared, depending on how you will modify your particular solution. Now, if you will modify the particular solution class, this would be the looks of it. So, the original is only, doesn't contain this one. The original doesn't contain the x. Okay, it's only like this. So, now you have multiplied it with the x. That way, you will be able to modify it. So, now you could see, you can compare that this is now totally different than this. Now, since the two are already totally different, then you can do the rest of the procedures that you have learned in terms of finding the values of the undetermined coefficients here in this particular example, A and B. Okay, so then the rest of the procedures I leave to you. So you need to modify by multiplying in terms of the independent variable, and you will find the undetermined coefficient by again differentiating your yp, substituting it in the original DE, and determining the values of the undetermined coefficients. Okay. Now we go to the next example, and that would be this time a polynomial and a cosine function. So you will still need to write the auxiliary equation based on what's written here on the left side. So this would be your auxiliary equation, and it will yield repeated roots. So if we have modified in the previous example your particular solution, because we want it to be unique from the terms of your complementary solution, this time we modified the term or a term in your complementary solution to make it unique from the other one. So you know how to modify. We multiply in terms of the independent variables. In this case, we modify the second term here by multiplying it with x. Okay, so that's your yc, but your yp is to be written in this form. So since you have a cosine function, it should have the cosine and sine function, and since you have a polynomial, this was shown a while ago, you should have an ax plus b because your polynomial is a first degree polynomial. In here, you should have a cx plus d. You need to differentiate twice because you have until the second derivative. So this is the part where we're in the process of method of undetermined coefficient is very long. Because if you have a product of two expressions and you need to differentiate it, you have two terms equivalent to that particular derivative. In here, you also have 2. Okay, so you have here 2 and here 2 for their derivatives. When you perform the second differentiation, you have 2 for this, you have 2 for this, you have 1 for this, and 1 for this. That would be all in all 6. In this case, I have already simplified it, and you are now left with 4 terms. The thing is, you need to substitute these 3, the second derivative, the first derivative, and the form of the particular solution to your original DE, and copy the right side for you to be able to find all 4 undetermined coefficients. So in this case, we need to equate coefficients of cosine 3x and sine 3x. The right side doesn't have a sine 3x, but you still need to do that. So initially, you will have something like this. If you equate coefficients of cosine 3x, this will be the resulting expression. Now, from this equation, you need to equate coefficients of x and simplify. So if it's in terms of x, you have a negative 9a, a 6c, and a 4a equated to 1. If we simplify this, the answer will be negative 5a plus 6c equal to 1. From this same equation, we equate constants. So you have a negative 9b, a 6c, a 2a, a 6d, and a 4b. If we simplify, this would be 2a minus 5b plus 6c plus 6d is 0 because we don't have a constant here. You do the same after you have equated coefficients of the sine 3x in the original equation. So if we equate coefficients of sine 3x, it would be this. If we equate coefficients of x in this equation, it would be this, simplified to this. If we equate constants, you will have 6a minus 9d minus 6b plus 2c plus 4d. Simplified is negative 6a minus 6b plus 2c minus 5d. Now, you will need to work with 4 equations simultaneously to determine the values of the 4 undetermined coefficients. If you're done determining the undetermined coefficients, then all you have to do is substitute those coefficients in your particular solution. This is your particular solution, and sum it up together with the complementary solution. This is just but short because I have written everything already. But if you're the one who's doing this will entail time, depending on your skill to differentiate and depending on how well you work on equations manually. But I think you have your calculators to do that for you, so it would be very easy. Okay? So this is how you find solutions of non-homogeneous higher order differential equations with constant coefficients in which the right side is a product of 2 different functions. Now, the 7th example here is a combination of everything we have discussed. So, it could be any combination of those. In here, you have exponential. In there, you have sine. And here, you have a product of an exponential and cosine function. How do you find the solution of this particular differential equation? You need to process it piece by piece. Like this left side should be only first equated with this. Then again, this should only be equated to this. And this should be equated to this. The purpose is for each of these, shall I say, partial DEs, coming from this original DE, you'll be able to determine their own partial particular solution. So let's say you will have a particular solution here. Let's say yp1, this will be yp2, and this will have y, by the way, this is yp1, this will be yp2 constituting 2 terms, sine and cosine, and this would be your yp3, which will constitute also 2 terms, product of exponential function and cosine and exponential function and sine. If you will find the values of the undetermined coefficients, it would be this. So the thing that I have written here actually is just the particular solution based on the 3 terms that you see on the right side of this DE. So the complete solution would still need the complementary solution. And this one is similar to the ones that I gave you in the previous example. So you only need to copy the complementary solution in those particular example. Then add it with this, that would then be your complete solution. This is the method of undetermined coefficient. It's uncomplicated. However, it could be very lengthy. The procedure could be very lengthy. It doesn't need any integration, but number 1 problem with this method is it has 2 restrictions. Number 1 restriction is the g of x. So it can only handle the functions that I have given here. Everything that I've presented here is already complete in terms of the different functions that should or could be handled by the method. Second is it can only process homogeneous or rather non-homogeneous higher order differential equations with constant coefficients. So if the coefficients are not constants, this method will not work anymore. So that would wait for the method that will still be discussed to you next week. That would be Wednesday, because this coming Friday, you will have your quiz on homogeneous higher order differential equations with constant coefficients. Okay? Thank you, class.